Okay, our last speaker of the session is Professor Eva Andrei from Rutgers, who will tell us about moire and more crystals, intercrystals, and quasicrystals.
Thank you for inviting me. It's a real pleasure to be here. And Allan and I go back a long time with friendship, physics, and shopping. And for this special occasion, I thought he deserved to get a Moire is Different t-shirt. So what I'm going to tell you about today is the Moire. So I'm going to start with the let me see, this pointer is not working. Let me get the pointer to work here. Okay. Oops. Sorry about this. Okay. Let's see if the pointer works. It's not working. Okay, do we have a stick or something? Okay. Okay, let's go without pointer. Okay, so I'm going to start with when you take two atomic crystals and superpose them, and to create a moire pattern, which is a super period, it turns out that when you look at the density of state of the band structure, this moire pattern actually creates a periodic potential that changes the band structure. And all sorts of interesting things can happen as a function of the twist. In particular, you can get flat bands, you can get Van Hoff singularities, correlated states, etc. So I'm going to start with a little bit of a review over that, and then I'm going to move on. Okay, so if superposing two crystals is so interesting, what happens if you superpose two moire patterns on top of each other? And it turns out that there are many surprises and many interesting things happen that kept us busy for quite a while. And I think there's a lot more work to be done. In particular, we get a different two-dimensional crystals that we can change, quasi-crystal, intercrystal, which I'm going to explain what I mean, and crystals. And we can also get new kinds of correlated states. So let's get started. Since we are at the celebration here, let's get started with a little bit of history. Okay, first, the most important people are the people who did the work. The top row here are the STM team. The bottom row is our theory collaborators at Rutgers. Okay, a little bit of history. So moire patterns are not new. Atomic moire patterns actually were the first thing that was discovered when the STM was invented. People started looking at graphite, and lo and behold, they saw these huge super periods that we now call moire patterns. This is a term borrowed from textiles. But it took another almost 2 decades to figure out that, in fact, not only does the superposing create very pretty patterns, is this a pointer here? Okay. Yes, okay. Not only does it create pretty patterns, but actually it changes the band structure. And when you change the twist between the layers, you start out when the twist is larger than 10 degrees, you don't see anything. You see the V-shaped band structure. This is a density of state. This is an STM measurement that was done in our group on CVD graphene that was suspended on a transmission electron microscope grid, and then we walked the STM on top of it. Now, the reason we needed to suspend it is because at the time, the only way we could look at graphene was to put it on silicon dioxide, and the substrate is terrible. It has lots of dangling bonds. It really interferes with the band structure. So we had to suspend our samples to look at what's going on. So this is one of the things that we did. Since it's a TM grid, we needed a huge sample, so we couldn't just do an exfoliated sample. We used CVD graphene. And to our very our surprise, we are looking for something totally different. We are looking for Landau levels and all sorts of other things. To our surprise, we saw these patterns, and it turned out that in that sample, we had many, many different twist angles. And when we looked at the band structure, which nobody thought of looking at before, we saw that as a function of the twist angle, as you decrease the twist angle, the band structure is reconstructed. So you go down to 3.5 degree, you see the Van Hoff singularities pop out. They're 450 millivolts apart. 1.8 degree, they get closer. And at 1.16, they actually overlapped. And it looked like we created a charge density wave. It looked like we have a little gap here in this flat band. And this is where Rafi and Allan came in, and then they showed, using what's now known as the chiral model, using tight binding, that you do indeed get these Van Hoff singularities, and when they merge, they merge at this magic angle, and now this iconic magic angle. Now, I didn't know about this bonus question that Rafi mentioned. So he could have actually told the student that people have solved the band structure of twisted bilayer graphene. Back in 2007, Lopez and Castroneto, they actually did get the band structure, but they missed out on the Van Hoff singularities. And later on, this Chilean group, Suarez Morel, actually did get the Van Hoff singularity, did get the flat band, but they got a kind of wrong twist angles because they assumed that you have to use Bloch theorem, you have to be periodic. So they use periodic structure. But the bottom line is that, at the time, this was kind of really esoteric. Why do you work on things like this? And it took quite a while for this to catch on. And in a moment, I'll tell you why that is. See, here is some experimental landmark from the beginning, which was kind of, new and esoteric. But then people figured out that, you don't have to suspend the sample. And this was work by the Columbia group. And they showed that if you use boron nitride, that's when boron nitride came in, that the boron grown by the Japanese group, Watanabe and Taniguchi. If you use boron nitride, you can actually put your graphene on a without suspending it. And they were able to observe the fractional quantum Hall effect on a non-suspended sample, whereas before we had to suspend the sample. Next came the big breakthrough, and that happened here at Austin from Emmanuel Totuk's group, who figured out a way to control the twist angle, because we couldn't. We had to walk across the sample and find different twist angles. And so now we had the twistronic toolbox. Now everything was possible. You could look at the band structure, you could control the twist angle. And that's when the big, this was the big event that happened in 2018 at the March meeting. Pablo announced this result, and they had assigned to them a tiny little room. So we had to actually, I was chair of the DCMP at the time. We had to find a bigger room. So what we did, we projected his talk across the entire meeting, and people were hanging in the corridors to see this, because by putting together this device, they managed to see superconductivity. This is pretty boring superconductivity. It was at what, 1 degree, but it was pretty interesting because it happened in carbon. Okay, and so that actually broke the floodgates, and this is all history. All sorts of new phenomena were discovered. So what I'm going to focus on today is one that actually Allan was involved in, an experimental result that came from Goldhaber-Gordon's group and Andrea Young, that saw the quantum anomalous Hall effect in twisted bilayer graphene, magic angle twisted bilayer graphene, where you break the inversion symmetry by depositing on boron nitride, okay, with perfectly aligning it with boron nitride. But a little bit about Moiré. So, okay, we all know that when you put two patterns together with a twist, you get a Moiré pattern with the super period. It's inversely proportional to a twist angle. What is maybe less known is that if you shift the layers, as you see here, the pattern doesn't change. And this is a real gift to experimentalists because it doesn't matter how you align them. All that matters is the twist. So what are we looking at here? First of all, the bright spots that we see in STM are what we have the AA configuration, where every atom in the top layers, every atom in the top layer sits on a corresponding one in the bottom layer. There's a BA configuration where every B sublattice atom sits on the A sublattice in the bottom layer and vice versa. So this is the pattern that you create. So these are the AA regions. When you look at topography, these are bright because the electronic wave function is focused there. Now, when you do a little calculation, you calculate the registry index, which gives you the ratio of the areas of the bright and dark regions. You see that the AA and the ABs and BAs take up about the same area. And it doesn't matter the twist angle. No matter what the twist angle is, they always take up the same area. But in fact, there is some energetics that goes on here. And it turns out that the AA configuration is extremely expensive. It's about 20 millivolts per atom that you have to pay to have an AA configuration. AB and BA are much cheaper. This is the Bernal stacking, and this is the saddle point here. So in fact, when you go to small twist angle, it really pays, where the Moiré is very large, it pays to shrink the AA region at the expense of building up strain. Okay, and that is energetically favorable. And in fact, when you go to 0.3 degrees, these AA regions become tiny. And this is theory, but in experiment, that's exactly what you see. Okay, so there is a lot of action going in there. It is not a static kind of crystal. Okay, so if you calculate the band structure without taking into account this alignment, this relaxation, you see that there is a flat band, but it is continuously connected to the remote band. So such a flat band is not very useful for getting correlated state. You really want it to be separated from the remote band. So in fact, what the relaxation does, it opens up a nice band, a nice gap to the remote bands, and then a lot of interesting things can happen if you are able to bring the Fermi level within that flat band. Okay, so this is. So here, so we have an isolated flat band. Okay, of course, you have 8 orbitals per Moiré cell, 2 for spins, 2 for K-valley, and 2 for sublattice. If you gate the sample with a gate voltage, you can throw in electrons and change the Fermi level and bring it into the flat band or bring it outside of the flat band. So you can explore this band structure because the electronic density is so small that, you know, with a small gate voltage, you can actually change the Fermi level by a little bit as opposed to what would happen if you have a regular metal. Okay, so here is a little bit of kind of theory. So if you write down the Hamiltonian in the K-valley here, so for layer 1 is in pink, layer 2 is in green, and the off-diagonal blocks are the tunneling between the 2 layers. So this looks pretty complicated, but if we do a little change of basis here, if we move from the layer basis to the sublattice basis, something very interesting happens. And now you see that in the top layer, this is the A sublattice Hamiltonian. You have a Dirac-Weil Hamiltonian with a gauge field that has opposite signs in the A and B sublattice. This is a gauge field. And then you can calculate that this will give you what we call the pseudomagnetic field. It is, of course, very inhomogeneous, but the maximum value is about 120 Tesla, one can estimate, and they have opposite signs in the two sublattices. That means that you will have Landau level or pseudo Landau levels without applying a magnetic field. Okay, so and this pseudomagnetic field points in opposite direction in the two sublattices. So this was for the K valley. So you see here, sublattice A, the pseudomagnetic field points up, or we can say the Chern number is +1, and sublattice B, it points down. Of course, we cannot forget the K prime valley, and there everything is time reversal symmetric. So in the K prime valley, we have sublattice A has a pseudomagnetic field that points down, sublattice B has a pseudomagnetic field that points up, okay? So now we can write these 8 states. We can label them by spin, valley, sublattice, and Chern, but they're all degenerate. So there is topology inside this flat band, but you cannot see it because it's hidden inside this degeneracy. So, and this degeneracy is very strongly protected by C2Z inversion symmetry in plane and time reversal. So unless you break those, you will never see any interesting correlated states. You have to break those. So one way to break them is to break the inversion symmetry with a substrate, as I'm going to show you in a moment. The other one is, of course, to break the time reversal symmetry as a magnetic field. So let me move to how we break the symmetry with a substrate. So here we have, on the left, we have graphene. So we have carbon on every sublattice. And on the right, we have boron nitride, which is a sister crystal. It's exactly like graphene, except that it has different atoms on the different sublattices. And therefore, it's such a good insulator. It's a 6 electron volt insulator. So now if I superpose the two and I naively just do this, I see that, of course, you break the symmetry, and the carbon that sits on top of boron is more stable, has a lower energy than carbon that sits on nitrogen. So now we have split those levels, the degenerate level, into these pink levels where carbon sits on boron and the blue level where carbon sits on nitrogen. And now we can start throwing in electrons. If you throw in an odd number of electrons, you must end up with a finite Chern number. You can see the topology. Okay, so let's say that we throw in 3 electrons, and this is what Goldhaber-Gordon and Andrei Young did. So they throw in, now you see, you throw 3 electrons, you still have a degeneracy. You can either have a +1 Chern number or -1 Chern number. You further break the degeneracy with a magnetic field, and that's what they did. They trained the system with a positive magnetic field, and look at and you see they have a perfectly quantized quantum Hall effect, +1, and then there's hysteresis. They change the orientation of the magnetic field. The Hall in one case sits in the K valley, and in the other case sits in the K prime valley. So you've switched valleys. So of course you see the quantum anomalous Hall effect with in the 2 different values. So this is all very beautiful, but then, and it agrees with naive theory, but that's when Allan and other people notice, wait a minute, how can that be possible? Because in fact, contrary to what I drew here, graphene and boron nitride are not identical. They have slightly mismatched lattice constant. And in fact, because of that, it's very, very difficult to really break the inversion symmetry. So they have a small lattice mismatch, about a couple of % here. And therefore, as Allan showed and others, there's only, the twist angle between the graphene, the bilayer graphene with theta GG, and the twist angle between the bottom layer graphene and boron nitride, the only way you can align them if you have these 3 co-prime integers multiplied by 1.1 degree in one case and 0.55 in the other case. And then if you do have that very precise alignment, sure enough, you're going to be able to break the inversion symmetry. However, how can we do that experimentally? And now I'm going to show you why this is so challenging. Experimentally, we know very well how to twist graphene on graphene, because we do it with the same graphene layer. We cut it in two, we superpose and we twist, but you can't do that with boron nitride. With boron nitride, it's very difficult to get a precise alignment with boron nitride. And here is an example. Okay, here's my first layer of graphene. I'm bringing on top of it the second layer of graphene. Okay, I'm twisting it by 1.1 degrees. I think that the moire pattern shows up. And now I'm bringing in the boron nitride on top at 0.55 degrees, and I'm twisting it. Okay, so this is my super moire with the two moires. And now, as an experimentalist, I cannot precisely, let's say that I have a little shift. Okay, look what happens. You see, when I shifted, you shifted by one atomic size, and the whole pattern changes, unlike twisted bilayer graphene. This is very challenging experimentally. Okay, and as Allan noticed that what's going on here, so here what he plots here is the chirality. So red is Chern number +1, blue is -1, green is 0, and the scales here are an offset from perfect alignment here in angstroms, on the x direction, y direction. So if you're off by an angstrom from the center here to the right, you end up with Chern number 0. If you're off by an angstrom and a half, your Chern number, your Chern number -1. So then the question is, how come these people with doing transport over a macroscopic sample, like a few microns for us, this is macroscopic, how were they able to observe the quantum anomalous Hall effect? What was going on? So that's what motivated us to look into it with scanning tunneling microscopy. Okay, so this is being written up. So some of what I'm going to tell you is going to be in this preprint, which is going to go on the archive soon, maybe after this conference. Okay, so this is the experiment. So we had twisted bilayer graphene on boron nitride. We did our best to try to align it, and then we expected to see something. What the transport people have seen, align boron nitride to twisted bilayer graphene, and indeed we have a sample here that is commensurate. Okay, 1-to-1 commensurate, exactly what they were supposed to have seen. But then we go to a different region of the sample. It looks totally different. It's strain commensurate. Moire of moire. Moire of moire of moire. Moire quasicrystal. Moire intercrystal. I'm going to explain in a moment what that means. So, first of all, what are we looking at? So if you just put graphene on boron nitride, you see these dark spots here. These dark spots correspond to the lowest energy state where carbon is exactly aligned to boron, and there's a bright halo around it. When you do twisted bilayer graphene by itself, the brightest region here are the AA regions. So now you put the two on top of each other, and I put it in a, let's say, configuration where the lattice spacing of twisted bilayer graphene is 3 times that of boron nitride. So you see that the bright spots are between every 2 bright spots, we have a dark spot. Okay, so now you go to a particular sample, and you can see the bright spot and the dark spot, and immediately you can figure out, okay, what is LGG? The lattice spacing for twisted bilayer graphene, and the distance between the dark spots gives you the lattice spacing graphene boron nitride. And then we can go to reciprocal space, calculate KGG, KGBN, calculate the actual twist angle, get the strain. There's a lot of stuff that we can get out of this. Okay. So here we have a phase diagram. On the vertical axis, I have the lattice spacing of graphene boron nitride. On the horizontal axis, graphene, and these lines are commensuration lines. So there is one spot of perfect this is called the rigid lattice alignment. This is these are the numbers that Allan had in his paper, but you can also have alignments 2 to 1, 3 to 1, and this is all theory here. Now, by the way, rigid lattice alignment cannot happen. You don't have a point of rigid lattice alignment if you have 3 identical layers, like for 3 graphene layers on top of it. You have to have 2 and 1 or something like this. So, okay. So now here we have a sample that's exactly perfectly rigidly aligned, no strain in it. But then we have another sample. And this one is completely off that rigid lattice commensurate, but it's still perfectly commensurate. And you can see by looking at the Fourier transform, you can see the inverse lattice vectors, and they are way from the rigid lattice alignment, and we can calculate the strain is about 0.3 degrees. And then we look at more samples, and we have a whole array of them, and they're all along this line, and they're way far, up to 20% deviation from rigid lattice alignment. So it looks like this crystal likes to relax to the 1-to-1 alignment. How far can that go? So we find what we call a basin of attraction. There's absolutely no points around it, and we can actually understand it with a little bit of theory. But then we find many other lattices which are not aligned. They are quasi-crystal, intercrystal, they're quasi-periodic. We have a few other periodic ones. By the way, there's no basis of attraction for anything but the 1-1. So it really doesn't pay to align when you're 2-to-1 or 3-to-1. This is the only place where we get rigid lattice alignment. Okay, so the energetics of self-alignment are pretty obvious. This was calculated by our theory collaborators, and this is a sample. It's based on a Frankel-Kantarova model. So you model the AA regions as balls and with springs that sit in this van der Waals potential here, in this Moiré potential, and then you crank out. You can calculate the energy, the elastic energy that it costs to jump for one of these springs to go into a minimum for all of them, and then you calculate the gain in potential energy. You minimize, and you find that of course, when you are exactly at rigid lattice alignment, you get infinite size domain, but when you're off it, you get finite size domain. And you get domains with domain boundaries. And you see, and here we just plotted, okay, how far are you from rigid lattice alignment? 0.22 degrees, you see hardly anything. You get closer, 0.33 degrees, something starts showing up. At 0.5 degrees, which you're 10% away from rigid lattice alignment, you see a nice domain forming. And in this domain, we have 1-to-1 alignment. And you see the color scheme here tells us that the redder you are, the larger the strain. So basically, it stretches until it doesn't pay anymore, and then it gives. And that gives you a domain boundary, and then the whole thing starts over again. So this is the basic idea. Now, do we see this experimentally? So here we have a commensurate lattice, the 1-to-1 commensurate lattice. And just to make this clearer, I'm just highlighting a domain boundary. Now in blue, this one here is a tensile boundary where you stretch, where the displacement is perpendicular to the boundary. And here we have a shear boundary. But in here we have a 1-to-1 commensurate crystal. And if you look inside, if you do a density of state maps and you look and as a function of at the filling of 3, this is the filling where the transport people saw the quantum anomalous Hall effect. You see that one row below this missing row here. So inside the commensurate region, you have something that looks like an edge state. And if you take spectra across this line, you see that when you cross this line, you get something that looks like a mid-gap state. Okay, we do not know yet what it is. We're still working on this. And this could be a candidate for those chiral edge states that give rise to the quantum anomalous Hall effect. Now, to get a little bit more insight into it, we again looked at the topography and we mark the AA regions where the wave function like to sit with the black spots. And then we do what the transport people did. We trained a sample with half a Tesla positive field and come back to 0 field. And we look, where is the wave function now? And you see that we have the maximum, the yellow circles here are where the AA regions were seen in topography, but the maximum of the wave function has now shifted to the AB sides. And when you take a Fourier transform of this, you see that you have enhancement of scattering perpendicular to the boundary, and it's kind of suppressed away from it. And next we go to the other side of the magnetic field. We apply a negative magnetic field. We train it with minus 500 millitesla. And now the wave function has shifted in another direction, closer to the BA side. And the Fourier peak here has kind of turned by 60 degrees. Now unfortunately, this sample kind of crashed. So we have to make a new sample and to look at QPI and look at the energy dependence. If this is an edge state response with a chiral edge state, we should see slopes of the QPI, of the energy as a function of momentum, that are in opposite direction when you train the sample, but we are not there yet. Okay, so this is the speculation. Maybe these are the states that are responsible for the observed anomalous quantum Hall effect. So let me move to the next part here, the quasi-periodic crystal. So we've all learned as undergraduates that you have Bravais crystal. When you have a Bravais crystal, they're spanned by 2 lattice vectors. The number of lattice vectors that span a crystal is called the rank, so it's rank 2. And of course, you have translational symmetry. Therefore, you have a block states, you have crystal momentum, you can define the Brillouin zone, all the wonderful things that we like to do. And there's long range order that gives you sharp Bragg peaks. You have you have only 4 allowed rotational symmetries. Okay. Now, what happens when you have quasi-periodic structures? So first of all, they're always spanned, of course, by more than 2 vectors. It's a rank that's larger than 2. There's no translational symmetry. Therefore, we're losing the main tool of solid state physics, which is Bloch theorem. You have to get around it. No Bloch theorem, no crystal momentum, no band structure. But you still have long range order. That means you still have sharp Bragg peaks, but nothing else. So in this category, quasi-periodic crystals, there's 2 kinds. One is a quasi-crystal, which we all know and love, and that is has all these properties here, and it must have Bravais forbidden symmetries, 5, 2, 12, 5, 7, 12, whatever. And the other category, they have all the properties that I listed above, but they do not have a Bravais forbidden symmetry. It has the same symmetries before. Why do I do, and that's why we call them intercrystal, then between crystal and quasi-crystal. Now, the reason I'm going to these pains to distinguish between them is that when we first submitted this paper, and we made a mistake of in the title writing quasi-crystal instead of quasi-periodic crystal. So we were completely rejected because they said, oh, you don't see it. In order to see quasi-crystal, you must have a forbidden Bravais symmetry, and that's it. You cannot. And that's it, and nothing else matters. So then I went to Paul Steinhardt, who actually invented the concept. And it turns out that he's very possessive about quasi-crystal. He said, there's no way you can call these guys quasi-crystal. You have to find something else. Okay, so you cannot call these guys quasi-crystal because you have a six-fold symmetry. So we have to come up with something else. So that's why we call them intercrystal. Okay. So here is an example of an intercrystal. So this is the topography, and this is the Fourier transform. And you see the blue lines are the reciprocal lattice vector of the GBN, and the blue one of the GG. And in this particular one, the GG is at 30 degrees to the GBN. And quasi-periodicity, for quasi-periodicity, the projections of one of the vectors on the other has to be irrational. So obviously, in this particular case, it's pretty obvious. Theta is 30 degrees, so we have a irrational projection. And here is our quasi-crystal. Now, why is this a quasi-crystal? So here is the KGG and KGBN, blue and white. And now you take a linear combination of KGG and KGBN, and I'm getting this yellow one. So this yellow one, there's a very special case here. They're exactly the same length as the GBN one, but they're 30 degrees to it. So now I have a dodecahedron, 12-fold symmetry for Bravais forbidden symmetry. So Paul Steinhardt is happy. So it is not perfect quasi-crystal. It's a little bit distorted, but that's as good as we can get it. So just to summarize here, what we want to look at is the electronic properties. Now here we have the perfectly aligned crystal, and we see that no matter what the energy is, where you look at the density of state map, you have the six-fold symmetry. Okay, so this is the Moiré K vector, and when we look at the gate-dependent spectroscopy, you see a flat band here. When the Fermi energy is in the flat band, you open a gap here, and you can see this more precisely here. So when the Fermi energy outside of the band, it's narrow, it broadens when you bring it into the band. All the things, beautiful things that we saw on just twisted bilayer graphene without being aligned to boron nitride. And of course, because we have many different angles, the length, the region over which you actually have this flat band will depend on the twist angle, because we have a whole new family of aligned crystal. Okay, so here is wait. So what does theory tell us about the quasi-periodic potential? You should have, most of the wave function should be localized. There's a thin set of spectra where the waves are delocalized. You get the different symmetric states, you get different symmetries. You have a fractal energy spec, multifractal wave function, strong correlation, topology, quasi-periodic, a lot of very interesting things that are predicted. And this is just a subset of the paper. And this is all open. Experimentally, you cannot get these quasi-crystals except when you do this. In nature, they're very rare, and they're not two-dimensional. So here we have a synthetic platform to create quasi-periodic structure. So I'm almost done. Okay, so here we have the same thing, but now for an intercrystal. So this is the topography, and I'm doing density of state map as a function of energy, and now it's very different. You see stripes, you see squares. The Fourier transform, you've lost the six-fold symmetry. You go from one symmetry to another, and then. Okay, so this is the zoom into this region of the Fourier transform. And if I do the gate-dependent spectroscopy now, it's very, very different. I do still have a flat band. I still open a gap when the Fermi energy is in, but it's very different from the standard TVG. And then we can do the same for our quasi-crystal. Again, the symmetry is completely lost. Every different energy has different symmetries, because this wave function now scatters off a non-periodic potential. So there are all sorts of interference, and and destructive and constructive interference. So this is our um, so now when we look at the spectroscopy again, it's very, very different. We kind of, maybe we have a gap, but maybe we have a flat band. And now we have dozens of samples and every of regions with different quasi intercrystals, and the band structures are crazy. And I'm not sure I'm allowed to call this band structure. So this brings me to the summary. The take-home message is that lattice relaxation favors one-to-one commensurate moire crystals. Domain walls host 1D conducting edge states. And when you have quasi-periodic moire crystals, you have two kinds, the intercrystal and quasi-crystals. I don't think there's a fundamental difference between them. It's just to placate Paul Steinhardt. I actually don't know if there is a real difference. They host flat bands, correlated states, and the jury's still out, and there's lots and lots of things that remain to be done. And thank you for your attention.